Good afternoon, everyone. Welcome to Chase Plastics Chase the Knowledge webinar on outdoor plastics. My name is Sherry Cudd. I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your busy day to attend. I've got a few quick housekeeping items before we begin today. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar, which is at the top right. If you'd rather ask your question verbally, please raise your hand in the toolbar and I will unmute you and call on you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of this presentation, our product line card, and information on our technical engineering team in the materials section, again, the top right-hand section, during the presentation. If you are attending live, a certificate of completion and a copy of the recording or a copy of the webinar recording will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of the presentation and her handouts today. We would greatly appreciate it if you could complete the survey at the end so that we can improve future webinars for you and cover the topics that interest you the most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page, including our next one that we will schedule for December. You can now subscribe or invite coworkers to subscribe to receive notifications of future Chase the Knowledge webinars, and that's where that red arrow is pointing to on the page. Another great technical resource is our Chase the Knowledge blog on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. In addition to our presenter, Andrea Kendrick, who I will introduce here in just a moment, we also have Jason Merkel, Technical Manager, on hand to answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise that she brings to the table. So without further ado, Andrea.
Hey, good afternoon. Andrea Kendrick here. We're going to go over outdoor plastics today. So for our agenda, we're going to go over weathering, kind of what the term means, a little more information on it. Then we're going to go over solar radiation as the big main key component of weathering. We're going to go over the degradation process, so kind of what happens when it's being attacked. We're going to go over weathering damage, what that looks like, and then how we test it. Or can test it to see how it's performing. We'll talk about polymer performance briefly. We'll go over some of the materials and in general how they tend to do. And then we'll talk about a couple additives that can be used to help with weathering performance in our materials. So what is weathering? The definition specifically is the process of being worn by long exposure to the atmosphere or to the elements. And so if you put something outside, it's being exposed to the elements, it's going to wear down eventually. How long that takes? Well, that's a factor of a few different things. Weathering is a combination of primary and secondary factors, which we will go over, as well as in-use stresses on the part. So same with any other environment, stresses on the part are going to or could cause it to fail prematurely. That is certainly the case with weathering as well. Well, also polymeric materials, when they are exposed to the elements, they'll start to break down, they'll exhibit cracks. This is going to lead to failure sooner than had it not been outside. So basically you're weathering, wearing it, it's being attacked. And so how quickly it breaks down is based on a bunch of factors, but we'll go through some of them. So primary weathering factors, the ones that we're most concerned with and the ones that we test for when we do weathering testing, is going to be light. So we more accurately describe this as terrestrial solar radiation. A little bit of a mouthful, but solar radiation, which is going to be the total radiation from the sun that reaches the Earth's surface. We're not so concerned with any type of radiation from the sun that's not reaching the Earth's surface. The stuff that's blocked by our atmosphere and ozone, we're not so concerned about it because it's not affecting or attacking our products or us for that matter. Light, in this case, is made of photons that are traveling through space as waves. They come in the form of ultraviolet rays. They come in the form of visible rays and infrared wavelengths. And we'll talk briefly about those a little bit more as well. But the light that comes from the sun that we're experiencing are made up within those three different wavelength groups. Another primary factor is going to be temperature. So not only is the UV attack that we're concerned with, temperature change, thermal cycling can also affect how the material will weather and perform outdoors. And so we're worried about the degradation it can cause on its own from mechanical stress that's imparted on it from contracting and expanding. Expanding when it gets hot and contracting when it gets cold. It puts stress on the material. And so that's something we have to consider. It can also exacerbate the degradation process that begins after it's been attacked by the UV. And again, we'll go over kind of the process of degradation from UV in a few slides. And then lastly, moisture is another primary one that we're concerned with. So not only the temperature will expand and contract the material thermally, if the material is sensitive to picking up moisture, it will take in moisture, which will expand the inner layers of the part. And then when it becomes more of a dry spell, a little more dry season, it'll try to lose some of the moisture, which will then cause the surface to kind of split or crack as it's trying to resist moving or contracting back as the moisture is trying to leave. So all this to say the light, the temperature, and the moisture are all going to play a part in deteriorating our material when it is outside. Secondary weather factors. So again, as I mentioned a couple slides ago, weathering is a combination of your primary factors, which was the light, the heat, and the moisture we just talked about, as well as your secondary factors and in-use stresses. So secondary factors can play a part in the weathering of your material. They, however, are not typically captured when we do standard testing, but it doesn't mean it's not something that should be considered. So some other things unaccounted for that we don't typically test are going to be biological agents. So if there's fungus or microorganism growth, think of maybe the backside of a shed that doesn't get any of that light. You can start to have some growth on it that could impact performance of the material that's there. Your wind or sand erosion. So if you have sand particles that are hitting against the part or the wind that's hitting it excessively, it's going to start to wear the part much quicker than had that not been around. Air pollution can cause issues. And then chemicals. So any type of interaction with chemicals. Not typically are you testing that when you do your weathering testing. So if it comes in contact with, maybe you're wiping it down and cleaning it, maybe you're not testing that. Maybe you're not doing that in between your different rounds of UV exposure when you do your testing. Or maybe it's just incidental exposure. Fuel gets hit on it and then you wipe it off. But in that time, it could have attacked the material as well. So again, these are additional things that typically aren't accounted for when we do our testing, but it doesn't mean that it's not something that could be causing excessive weathering in your parts. Okay, and then in-use stresses, just a couple examples. So in areas where it gets cold enough to go through a freeze and thaw cycle, so here in Michigan, it gets cold enough that the water can expand when it's freezing. That's going to cause stress to our part, which could also cause it to fail prematurely. Mechanical constraints could be an issue. Think of window products. They're fixed in that mounted position. And so if you have a product that wants to either contract or expand, you're putting additional stress on it because it's confined to that space. And then lastly would be mechanical loads, as we should hopefully be paying attention to anytime we design a part or we're concerned about it. If you have a part that's going to see weight, it's going to be bearing weight, or maybe it's being compressed by another object or part, it's going to put additional stress on the part that could cause premature failing. So another thing that we should be considering. All things to consider when we're talking about, hey, I put a part outside and it failed. Well, there's a lot of things that we should be looking at to make sure that we're addressing them and we're finding what the problem really is. Okay. All right, so now diving more deep now into the actual solar radiation portion, the UV portion that we're concerned with. As mentioned a few slides ago, solar radiation is going to be between your infrared and your ultraviolet rays, and so that wavelength in between. And then the visible light is obviously then all of the stuff that we can see, the wavelengths in the color spectrum that we can see, infrared, and then ultraviolet, which we do not see, but is what is causing issues with our parts. So for radiation that hits the Earth's surface, again, infrared to ultraviolet, you're between 295 and 3000 nanometers. A nanometer for wavelength is a billionth of a meter, so 10 to the negative ninth. And so it's within that range that's hitting the Earth's surface. We're concerned with the UV portion, the UVB and the UVA portion that's hitting the Earth's surface, that's destroying parts. But only 4 to 7%, depending on where the sun's at, depending on what part of the atmosphere it's hitting, only 4 to 7% of the total radiation that hits the Earth's surface is ultraviolet. However, it is the cause for concern and what destroys our polymers. So we keep that in mind. Okay, so UV specifically, it comes in 3 different forms and wavelength ranges, I should say. UVA is in the 400 to 315 nanometer range. It is the less aggressive of them all. It creates more of a tanning effect that starts to change your pigments a little bit and can start to change the polymer a little bit. And then UVB, which is the more aggressive, it's a shorter wavelength, so it has higher energy. So the shorter your wavelengths, the higher energy they are, and so the more detriment to your materials and to you as a person, technically. But your UVB is going to be in the 315 to the 280 range. It's what creates a burning effect. It's what causes the severe polymer damage, or I should say initiates the degradation of your polymer. It also should be noted that the ozone has a cutoff layer. So if we switch back just briefly to the picture, you can see that UVC is blocked completely and only some of UVB gets in. That's because the ozone has a cutoff at about 295. So anything shorter than that, so the 280 to 100 nanometer of UVC, is completely blocked by the ozone. And so they exist, it's just not hitting us. So we're not as worried about it. So cut off at 295 with basically a 90-degree sun. So when the sun is directly overhead, it cuts off at about 295 wavelength. And then finally, UVC is going to be your 280 to 100. It has a germicidal effect. We have been known to harness that for technologies for some types of like sewage cleaning and stuff like that. And it's very aggressive. So there's not a ton of materials that resist it really well, but it's also not naturally occurring. And so if we're just worried about parts that are outside, we are not worried about that wavelength. It is the highest energy because of the shortest wavelength. And then these values are all dictated by CIE. So that association is the one that has dictated these ranges. Okay. So for UV radiation, if the energy of the photons that are in the UV rays, if they have enough energy, they are able to break bonds within the polymer or bond within the polymer. This is what caused the material to start to degrade. If you're looking at materials that have activation wavelengths that are pretty much entirely within the UVA range, which is the wavelength that is most common in our atmosphere, it's likely that you're going to have material that is most susceptible to damage. So your ABSs, your TPUs, very susceptible to UV damage. And we'll talk about a little bit more when we get into some of the other polymers. So the actual degradation process now, what happens? I put something outside, it ends up degrading over the course of that time. What has happened to it? So the actual process itself is that the photon within the UV wavelength, high energy, it's absorbed by what's known as a chromophore in the molecule of the polymer. So a chromophore is a site, it's basically a site that allows for the absorption of that radiation. It's the area that is most likely to absorb it, and it has to absorb it at that wavelength that it's being hit with, so the UVA or the UVB wavelength. A chromophore could be part of the polymer backbone, so part of the chemistry of the polymer itself. It could be a functional group within the polymer. It could be an additive, contamination, defect, could be any number of things that could cause it, but that particular group within the formulation or contamination, if it's contamination, that ends up within that polymer absorbs in the photon, and it starts to pick up that energy of the photon. Now what happens is that energy that's absorbed, it starts to create an excited state within the polymer. And if you don't dissipate it safely, the energy, what happens is it then breaks down the bonds and you start to create free radicals. Free radicals then will start to create other free radicals. It kind of starts this process of continuing to react. It can create further free radicals. These free radicals are unstable. There's a few different types that it can create. I didn't put the excessive amount of different types of free radicals that it creates within here. A little more chemistry than I think maybe we needed, but it will create further free radicals. They're unstable and they degrade with much less thermal or photonic energy. It doesn't take as much to start breaking them down because they're quite unstable. Some other reactions that could happen is you could also create stable compounds, but it results in stuff like change of color. So when you get your color change or other issues with it, it's because it's still reacting and that was the outcome. It created a stable portion on the material, but it is now discolored. They can also cross-link within the material. It can cause cross-linking to occur, which is going to result in your polymer embrittlement. So you have a polymer that can become embrittled, you have a polymer that can discolor pretty easily, and overall just start to break down and be attacked by this. The photons in the beginning from the UV energy that comes in, so your UV rays, they're only necessary to create the excited state and to initiate the first break. Once that's happened, the free radicals can continue to react and really only have to be driven by thermal energy. So when you talk about a material that's outside, if you're only testing the UV of it, and so you're just hitting it with UV rays in that wavelength, but you're not doing any type of thermal cycling, you're doing a disservice to how it's going to perform because the heat is going to continue to drive some of those processes and continue to make the damage worse. And if you're not testing that, it's not going to show that. So it might perform okay, and maybe it withstands it for a bit, and maybe it allows the photon to damage it and initiate that process. But if you don't do the thermal cycling when you're testing, you're not showing the full picture of what's going to happen when it's outside, specifically if it's outside in a fairly warm environment. Okay, so weathering, now we kind of know the process of what's happening. Of basically UV's attacking it, it's creating reactions within the material, thermal energy is continuing to create more. So then what happens, what does that look like if I'm looking at a part that's been outside? So generally in two categories, you're going to have appearance changes and you're going to have performance changes, or what you typically see. So appearance changes come in way of color shift, yellowing, can start to fade. You can get some hazing in clear polymers, so kind of looks more of like a cloudy versus very clear part. And then gloss loss, big one as well. And then for your performance changing, your loss of impact, loss of strength, embrittlement. So the performance itself starts to become hindered. So for appearance change, yellowing, color shift, all that, it's generally the most common way to use for weathering damage. It's what happens first. And so we see it first. We know that there's signs of damage that's occurring. And so we use coloring as a very common way to tell if it's being damaged or not. The most common color space that's widely accepted and used is CIE LAB. And so if you've seen any type of testing, if they're trying to show you a comparison between a weathered sample and a non-weathered sample, a lot of times they'll do either a delta E, which is an overall shift within this LAB space, or they'll do changes in the LAB values. And so within this color space, LAB defines L value as light to dark. So from 0 being black all the way up to 100 being white in nature. Then you have an A value, which is green or red. So if it's a negative A value, it's has a greenish color to it. If it's a positive A, it's got a reddish color to it. And then the one that we're most concerned with that we're going to see typically the biggest change in is the B value. And so if it's a negative B value, it's blue, bluish. And then if it's in the positive B value, it's yellow. So what will happen is when we start to degrade or there's damage to our materials, we're going to see an increase in the positive B value. And so we're going to see it start to yellow. It's going to show that if we do the testing, we take a sample we haven't weathered yet, we weather it, and we take a color reading, you're likely to see a decent change in yellow. I did mention briefly delta E. It's another standard. I don't have any text on here for specifically. Delta E is to give you one singular value to talk about the overall color shift within the material. Delta E is not a bad standard in that it gives you one value. It is a little misleading in certain cases, however, because we don't really know exactly what's happening. Did it change more yellow? Did it fade a lot and become more white? We don't know what specific value within the LAB space has been changed. We can guess and assume it's either faded or become more yellow, but we don't know that for sure. It's also, we're a little more sensitive to certain coloring than others. And so we'll see something a little more readily in a change than others. But it does give a quick, easy, here's one value to determine how different this part is compared to this one that's been weathered / damaged. So keep that in mind. There's some nuances to it, but it does provide a quick, easy way to determine that. So sometimes you'll see in testing information, you'll get a delta E value after weathering for a certain period of time. And so it gives you a value. Ideally, if it's possible, graphical data is always best. And I bring this up just because your one data value for delta E, it doesn't tell us after that period of time if we're in the process of rapidly losing our color or color shifting, or if it's plateaued, or if it's the case where it just hasn't used up. Maybe it's a UV stabilized grade and it's using an absorber and maybe it just hasn't used it at all up yet. So all this to say, delta E is a quick, easy way to do it. There are some nuances we need to be aware of, that it's not of the most optimal way to tell what's happening when we're talking about values. And ideally, if we could get a time, exposure versus performance graph, best way to be given information when we're talking about damage for color shift. Okay. And then also another one in terms of your appearance. So color shift is one, and then also gloss. So if you do a measurement for gloss reading, if you start to find that you're losing gloss, it could be a sign of damage. So gloss in general is a reflection. So the light will come in, the ray will come in, and it will bounce back. If it's a high gloss level product or surface, a lot of the light's going to be reflected back at you as the observer. Once it starts to degrade, the material starts to be attacked a little bit. It'll start to create cracks on the surface. As you can kind of see in the picture, it's kind of cracked. And what happens is now the light that hits it starts to become scattered. And so it's not reflected back directly at the observer. You're going to lose gloss and it's not going to come back as clean. It's going to be a lot more matte in appearance. And so you'll lose gloss and you'll lose color or change color pretty readily when a material is starting to exhibit some weather damage. Okay, so the other thing to note before we get fully into the testing is for the physical performance and loss of properties there, what you're going to find first is going to be your color shift first. Right at that surface where it's being attacked, you're going to see the color change or the gloss loss. It has to get a little bit further into kind of the bulk of the material or the product to crack it enough or to embrittle it enough to cause issues with performance. And so typically you'll see color shifts first, and then you'll start losing your property performance. So it's not a bad thing to also do property retention testing before and after exposure to get an idea of how it's performing. And so weathering, what it is, what it kind of looks like, what happens. Now, how do we test it? So we've talked about some of the color shift or gloss that you can look up, but how do we actually test it? How do we compare and see how these materials are doing? There's a couple different ways of doing it. You can do natural weathering. So we put it outside and we let it get weathered, or we can do lab testing. So for natural weathering, what they have a bunch of different setups, a whole bunch of different ways to do it. Um, you can do static sample racks. So these are the ones that are not going to move. They're just to stay where they're at. You can do ones with different angles. You can do ones with different backings. You can do racks that have glass covers over them, so it's more in line with filtered light. So if you have something like the interior of a car that's filtered through your windshield or your side windows, or in your house, so it's filtered through the window, either if you're in an office right now, as I am, filtered through the window, or in your house, filtered in through the windows of your house. So it gives a performance in that situation. They've also got static sample racks for accelerated testing. So they'll put mirrors on it. So it reflects back some of the natural sunlight. And so it's getting sunlight plus then some. And so generally on average, it sees about 5 times the amount compared to a standard rack with no mirrors. And so we can accelerate natural weathering a little bit in that way. We can add more to it. They'll also do static racks with mirrors as well as water sprays. So the water sprays will simulate a little bit of maybe some rainfall, maybe a little moisture. So it gives an additional factor that we can consider when we do testing that way. And then lastly, they have ones that are moving racks that are going to track the sun's path. So you can make sure you get the most sunlight during the day that you possibly can out of the material. And so our parts are not going to shift and follow the sun, but it makes the most out of the time that it's being spent out there, capturing a lot of that sunlight to really see how it's affecting the material. And there's 2 locations that are used very commonly. They're not the only ones. There are others specifically in the world that are used. But in the US, commonly benchmark location testing is done in Arizona. It's a very dry heat. There's no moisture really in the air that we're concerned with, but it has the highest radiation levels in the US. So highest radiation level, just dry heat, not much moisture. And then Florida is the other one. It has the wet heat. And so you'll see the most standard UV damage in Arizona, but without the additional factor of the moisture that you'll get from the air in Florida. So they'll do both. And so those are kind of your extremes when they do the testing. And so that kind of looks like here, if you're looking on the screen, you see down in Arizona, very high levels of radiation. And then Florida, still pretty high, not as high as Arizona, but it has the wetter heat that Arizona does not. Okay, and then testing inside of a lab now. So we don't have time to set it outside for, for year, 2 year, 3 year, however long you wanted the testing for, or how long you expect your product to last for. We don't have the time to do that. We have created and lab testing has been made to accelerate the process to get you data quicker versus waiting for the actual testing and actual allowing the material to sit outside for an extended period of time. There are some caveats to it and there's some nuances to testing in a lab, but we're doing our best to make appropriate correlations between the two so we can get an idea of our performance. So some comments on testing in a lab. It's suggested by some that it's really only great for ranking materials. So because you're missing other factors, maybe the thermal cycling is not, or dark cycling is not exactly in line with what you'd experience outside. The moisture is not going to be the same. You don't have any of the secondary factors that could be causing deterioration of your parts. But if you're using all of the same conditions and you're using different materials to compare them, you can start to kind of rank their performance. So you can say, hey, I tested this acrylic, it's performing better than this ABS or what have you. So it gives you a good idea on a kind of a ranking scale how it's going to perform without necessarily being the perfect image of what will happen when your part is outside. The other thing to note is that we can't perfectly make sunlight in a lab. And so based on studies for radiation dosage at benchmark locations, like in Florida, we can take an average of what it will experience over the year in Florida and then use it as a standard dose energy at a wavelength for that time to give it an idea of what it would be like. But because it's an average, some days where in Florida it's actually seeing higher radiation, some days where it's seeing less. So it could affect it as well. We're able to do an energy at a wavelength in a lab to give us the average, and it will get us close enough to give us an idea of how it will perform. So something like 3,500 kilojoules per meter squared at 340 nanometers is a decent performance level for a year in Florida to simulate that. So you can do testing like that. And then lastly, you can do it much quicker, which is kind of why we do it. So we can take a couple months of exposure within the lab and we can extrapolate the performance out to 12 months of exposure. The one thing to note about that is if it does have stabilizers in it, that short period of time might be before the stabilizers have been used up. So something like, again, a UV absorber, we'll talk briefly about them, but it gets used up in the process of protecting the material. So maybe in those 2 months, it hadn't been completely used up, so it shows good performance. So then when you extrapolate it out, it still shows good performance. But come month 3, maybe that we didn't test, the performance drops significantly because now there's nothing to protect the material anymore. So just another couple nuances to think about when we're doing testing or we're seeing testing on materials, what's really happening or what could be happening when we're looking at data for this. Okay, so some product performance. This is going to be kind of a good generic overview for the majority of these materials. Obviously, each material has a certain performance. Additives and UV stabilizers and colorants will play into its performance, as well as where the product's going to be. As you could tell, if your product is expected to be here in Michigan, there's additional factors that we have to consider versus if it's in Florida. So always more things to consider. But overall, generally speaking, stuff like your fluoropolymers, your PTFE, PVDFs, and then acrylics typically perform very well with little to no UV additive needed. So really good performance. Acrylic, excellent performance, UV. A handful of materials that perform really well if you stabilize them well. You stabilize them correctly for the activation wavelength that they're prone to being attacked at. If you stabilize them against that, really good performance. So polyethylene, propylene can be stabilized well to give really decent performance. TPOs, PVCs, we have vinyl siding, which we'll talk about just very briefly in a quick note on the next page, but vinyl siding clearly is used outside on your house, so good performance. ASA, nylons, aliphatic TPUs, so this would be a specialized TPU, does pretty good in UV performance when it's stabilized. PCASAs are okay, PCs are okay, PETs are all right, PCPPTs also pretty good. Then you start getting into the materials that really don't perform super well for our UV. So PCABSs, ABSs, really kind of a no-go the vast majority of the time. We really just don't recommend it. It's outside. Acetals, HIPs, PPEs, PPOs, and then aromatic TPUs, which are going to be more standard TPUs. So a little more information on some of the materials. ABS, it's very susceptible to photooxidation. It's going to yellow very quickly. It's going to discolor very quickly. So if you have something where you're concerned with it discoloring, ABS is not the material for you. Where possible, if it makes sense and you can get a good performance out of it, if we can replace ABS with ASA, ASA does have good performance. So where we can make that change, we try to, or we suggest that you try to anyway. So it will perform much better than ABS will. Acrylic, as we mentioned, really great inherent stability. If there's no stabilizers and it's used for an extended period of time outside, you might see that it starts to cloud or get a little hazy. But generally overall, very good performance. Nylons, they tend to hold their properties really well when they weather. Now, if you use a natural or a dyed material versus something like a black, you'll start to show yellowing pretty quickly. And so part of this is understanding what matters to you as an end result. Do we care if it discolors as long as it still performs well? Or can we have absolutely no color shift? And so that's part of the determining factor on if it's going to be okay or not in our application. But nylons, they weather well in terms of they'll retain their properties really well. So if you need outside for a long period of time doing whatever it's doing in application, it's going to do that. Maybe it'll just discolor a little bit. PCs will discolor fairly rapidly. I do have a little note on the following slide. Clear materials are harder generally. Acrylic is okay, but are generally harder with UV because if you need to stabilize them, you are a lot more limited on your options because you need to use something that most of the time you want the clear material because it is also clear. You'll start to lose some of the clarity if you use certain additives. So they can be more difficult to stabilize. And so they're kind of limited on the options they have available to you. So over time, PC though will start to discolor quite a bit and brittle and lose its gloss. It's worse in FR PCs. FR tends to, as an additive in really any of the materials, tend to make it a lot more difficult for it to perform with UV. It tends to be a site where it can be attacked. And so it can be an issue if you're wanting both UV and FR performance. Propylenes and ethylenes, the CH and CC bonds do not absorb the UV photons in the wavelength that comes into our atmosphere. But contaminations and other additives that are added into these materials do get attacked. And so that's the part that will be degraded. So if you give them a good stabilizer for whatever portion is going to be attacked, the contaminant and or the additive, it gives you pretty good performance for outside. 6, 7, 8, 9 years should be no problem, well stabilized. Polystyrene, it tends to yellow quickly, especially HIPS tends to yellow quickly. Kind of a similar concept with the ABS, with your rubber portion of it will tend to yellow quickly. Excuse me. Standard aromatic TPUs are also going to yellow pretty quickly, and then also yellow even more with temperature exposure. So outside where you've got the thermal cycling. So when we say standard TPU would be kind of your nice general purpose TPUs that you guys might think of. They make specialized grades of TPU that are kind of meant for more of the outdoor exposure type applications. Those again are specialized. So if you're using a standard TPU that you run or mold, it's not going to be the grade that you're thinking of, but they do make specialized grades that are better. PVC, poor performance by itself, but if you stabilize it, good performance. Again, as I kind of mentioned, think your vinyl siding of your house. Houses all over the place have them, so it performs well and for an extended period of time. And then something like a PETG, your PBTs, your PETs, they're going to tend to yellow pretty quickly. So they're going to discolor quite fast. Some things to consider, in addition to some of the other comments that I've also made. Weathering overall can be an inherent beginning property of a material, but we need to look at it as an overall system property, not just the material's inherent property. Because as soon as you add additives or colorants to it, it can affect how it's going to perform. So you have to consider that when we're talking about the overall performance. So if I test a certain material in natural with no colorant or no additive, and then I have my parts being made out of the same material, but maybe I add a green colorant or a blue colorant, whatever it might be, the performance could be different because of the additional colorant that's been added to it. Also, some of the colors are degraded by visible light. And so when the solar radiation is coming in, your outdoor radiation is hitting the part, the color within that, because the visible spectrum comes from the sunlight as well, it can start to attack it also. And so we have to keep that in mind. So UV is attacking generally the, your base materials, but some colors by design, because of the way they're meant to show off their color, can be attacked by visible light. So that is another thing to keep in mind. Also, if you are, in this case, weathering and only testing UV wavelengths, if it's a colored part, you could be doing a disservice by not testing the full visible spectrum as well as the UV spectrum, because the visible light could attack the color and discolor it. Specifically, if your overall goal is to make sure it doesn't color shift too much, well, you're not taking into account something that could very much cause that. So we got to keep that in mind. Weathering is more severe on clear grades. Again, it's difficult to stabilize something if we want to keep it clear. Adding stuff to clear materials tend to make it not so clear. And so you're kind of limited on your options there. And then darker colors, blacks, specifically if you're using stuff that's carbon black based, will hide your color shift better. I showed a little picture. The top piece is has not been weathered. The bottom piece has been weathered, but they used a dye, not a carbon black. And so I say darker and black, but I say carbon black because dyes don't really help with your UV resistance. So showed that picture to kind of show that difference. Okay. And then lastly for it, some additives. I'm not going to go into extensive detail. Part of it is because each individual material has a unique activation wavelength that I showed handful of slides back. And so each UV additive has to be specially formatted to make sure that it's saving the material from that wavelength. And so it's not typically as simple as just going, yeah, just throw UV additive in it. It doesn't work like that generally. It has certain wavelengths that it performs best in. So you have to pick the certain ones that are going to perform best in your material. So you can't just kind of start throwing ones in there and hope that they're going to work. But two of the main tapes that you're going to see are called UV absorbers. And so this is going to be your carbon black. It's going to be your TiO2 that makes parts white. What happens is it stops the initial degradation. So instead of absorbing in the radiation, it takes it and converts it into thermal energy. And so that way, and then it puts it back off. And so then it becomes non-destructive. It's not degrading that polymer chain. It's why sometimes you'll notice black parts, if they're made with carbon black and they're outside, tend to get hotter. It's because it's giving off that UV radiation. It's giving it back off as thermal energy. So black parts tend to get a little warmer outside. I'm sure we've all noticed that. And then the big one for the best performance it can give is going to be your hindered amine light stabilizers called HALs. They are free radical scavengers. So when we talked about the degradation process and how free radicals are formed and then they continue to react, and that's what causes all the damage and degradation, these go through and they scavenge for them and they convert them. And so it stops them before they can completely destroy the polymer chain. And so there's, again, a bunch of different options for them. Got to pick the ones that are going to be right for the material that you're looking for, but they're going to be your heavy duty UV stabilizers that are going to be added to your materials. And so they will help with that. So that's all I have for the additive portion. I mentioned briefly, and I do want to briefly mention one more time before my question slide. When we're talking about UV performance, it's important to understand what type of performance we're expecting or wanting out of our part. So if you are the end user or if you are working with the end user, is the answer that I need the material not to discolor at all? Because in that case, it's a much higher requirement, seeing as all of the attack is happening on the surface, which is where we're going to pick up the appearance of your part from. Is it we can't have the color shift, we can't have we can't lose gloss, we can't do anything about the surface. It needs to remain performing the way that it is, or is the important function that it actually functions the way that it needs to? Does it continue to still work the way that it's supposed to? And so those are questions that we want to make sure we understand. And so if you come to us as Chase or maybe even another company, hopefully, and you say, hey, I need a material that's good with UV, it's kind of a loaded question. We want to make sure we understand, okay, good with UV as in we can't have any discoloration. And then you come to me and you tell me you want it to be the brightest of pinks. Yeah, we're probably going to have a hard time keeping that color. It's probably going to want to be, it's probably going to degrade pretty quickly. But if you came to me and said, hey, I need it to be black and I want to keep it within a certain level of color shift, awesome. I'm sure that there would be something we could do as long as we're using a material that starts out with a pretty good, UV performance. And then on the flip side, hey, I don't actually really care if it discolors a bit or loses gloss or any of that, as long as it still performs the way it's supposed to. It's outside to do a job. I need it to do that job. That's a little bit easier because losing your property loss, as we mentioned, has to get into the bulk of the material before it causes that issue. And so that's a little bit easier to see. So things to consider always when we're talking about performance, materials, and environments that they are in. And that is all I had for you guys.
Wonderful. Thank you, Andrea. Great presentation, as always. At this time, if you have any questions, please type them in the questions section or raise your hand. I see we have a hand up, so we'll get to you here in just a moment, and I'll unmute your microphone. We have Jason Merkel, technical manager, who has been with Chase Plastics since 2012, on hand to assist Andrea with questions today. But as a reminder, as you type your questions, please complete the survey at the end of this webinar. Your responses will help shape future Chase the Knowledge webinar topics, and we welcome your feedback. Also, be sure to check out our blog page at chaseplastics.com/blogs and past webinar recordings and future webinar announcements and registration at chaseplastics.com/webinars. If you would like to have a custom Chase the Knowledge topic presented to your organization, please reach out to Andrea or myself and we can get that set up for you. So again, feel free to go ahead and type in your questions. Jason, do you want to take the hand up first or do you want to read questions first?
Take the hand first.
Okay, So, Errol, I'm going to unmute you here. I'm going to try to unmute you. Maybe you can unmute yourself and let's see if you can speak your question. Let's see here, Errol. Errol, are you there? Okay, we might be having some issues with that audio. Jason, why don't you go ahead and take the other questions and I'll see if I can get Errol's audio to work.
Okay, sounds good. Thanks, Sherry.
Mhm.
All right, Andrea. First question. Can you give us an idea of how much the average UV performance is improved by sunlight going through a double pane window? Do you gain 1x, 2x, or greater life as compared to normal exposure?
Ooh, that's a good question. In terms of times performance better, I don't know a value for it. It would probably also a little bit depend on the material. But to give a comparison, stuff like ABS, we would never put outside. Versus you have components within your car that are going through the window that are ABS and are able to be. It takes a while for it to damage it the way that it would outside. For those that have been in an older home and they've seen the classic example of the thermostat that's changed color, that was either an ABS or a PPE material that was not stabilized. But it took a few good years versus if you had taken that and put it directly outside within probably a couple weeks, it would have easily started to discolor. So an X value, I'm not entirely sure, but it's quite a difference that it makes.
Yeah, I would agree. It's going to be polymer specific as well as color specific. Just to expand upon that, if you've got a white or a tan part internally, whether it's in your kitchen or a thermostat example like Andrea mentioned, it's certainly going to have a significant boost by being indoors, even if the UV is coming in through a window. Where if it's a black part, it may last not just 2x, but 5x or 10x in some cases, depending on the polymer. So don't mean to be too gray in our answer there, but it is going to be kind of application and polymer and color specific. Next question, Andrea. Regarding stabilizer additives that wear down with time, do both UV absorbers and HALs degrade with time? And do either of them last for long periods of time outdoors?
Yeah, so the UV absorbers degrade with use, and so they're only good for so long, depending on how much of it that they're seeing. The HALs do eventually degrade down. They take a lot longer, so an extended period of time. So when people use the very vague, and I don't love the term, but 5 and 10 year UV stabilizer packages, it's using some form of a HAL for that. They're the advanced ones that are going to help with that. And it will eventually degrade down, but it takes a lot longer. And they renew themselves a little bit just by the basis of how they work and their chemistry, but it will eventually get used up.
Awesome, thank you. Next question is, what is the typical percentage of UV absorber or HALs that's used?
So typically it will also depend on the material and what you're trying to achieve out of it. If you need a more robust UV package for it, you want it to last an extended period of time or not. Generally speaking, for materials like your olefins and your nylons that perform pretty well in UV, as long as they're stabilized, generally speaking, carbon black 2% plus will work for a decent amount of time until you completely wear out the carbon black in it as the UV absorber. And then HALs are used at varying percentages, again, depending on the material, but they're generally used at smaller percentages as well.
For TPU specifically, which is better, UV absorber or a house system?
You're gonna find a little bit of an improvement with it. It will help it some. Um, they're just standard TPUs are not great for UV. So Hals in general are going to help the material more than an absorber will. They're more efficient at UV protection than UV absorbers will. And so you'll see you'll get more of an improvement with Hals for DPU, but most of the time TPU and manufacturers of TPU recognize that standard TPUs are not great for outdoor exposure, so they don't tend to put the time and effort into making a UV stabilize. The other thing that should be noted too, maybe, and this is the time for it, I guess, you don't typically go and just buy a HAL stabilizer and put it in a material. You can get some absorbers, which are going to be your carbon black and your TiO2, because they already come in form of then a colorant for your parts. But you don't typically just pick a HAL stabilizer off the shelf and then add it into your material. They're typically compounded in as a UV grade option from the manufacturers. And being that TPU is not great for it, they don't tend to make grades with it compounded in because they know that that's not really the market they're after because they know that it's not the best material for outdoor space.
Just as a side note, Andrea, on the prior question on typical percentage of absorber or HALs used, I pulled some data sheets for some of our additives. For more easily stabilized products like a polyolefin or a polycarbonate, we see dosage rates down below 1%, 0.75% roughly. And then for harder to stabilize products like maybe TPU or ABS, we see starting values anywhere from 2 to 3%, going upwards to 4 or 5% in some cases, just for sake of reference.
Okay, awesome. Thank you.
Next question, what is the minimum test that the pigment should be able, what is the minimum test that the pigment should pass to ensure its durability in an outdoor cooler?
An outdoor cooler. So I'm assuming the outside parts of it would be my guess. It comes down to the testing and what it needs to withstand comes down to what you expect and what you want out of it. So typically those types of standards and requirements come passed down to us from end users, and they tell us, hey, it needs to withstand this, or it needs to not discolor this, or it needs to hold property retention of this. And so that is generally dictated by someone that is people that are not us, and we do our best to accommodate what we can meet. So it would be for the cooler itself. Maybe I'm assuming like a Yeti cooler or something that's smaller. At first, I was thinking a large chest cooler, but maybe something smaller. That would come down to the expectation of the Arctics, the Yetis, the Igloos of the world, and what they have in terms of expectations for their material when their coolers are outside.
Yeah, I think, a question we try to ask pretty early on in some of these situations, especially with a consumer grade product like a cooler, is going to be, what's the OEM's expectations in terms of warranty and liability, and really how long they want these things to last. We know general consumer interest tends to be slated towards, unfortunately, colors that are harder to UV stabilize. So I'm sure you've all seen plenty of white coolers. White colorant is definitely not the easiest to stabilize because of its tendency to yellow or darken over time. And then when you look at the market for the brands that Andrea mentioned, from Yeti to Arctic to Igloo, there's everything from pink to turquoise to just about every color you can imagine nowadays. So a lot of the development cycle that we work through with OEMs and the molders or extrusion houses alike is to figure out, okay, what's really the end goal in terms of time that we want this to last, how much color shift, if any, is allowable, and what materials can kind of withstand that level of exposure. So in a lot of cases, we're talking minimum of a few years. No one's really expecting a 10-year-old cooler to look the same as it did, the way it came out of the box, so to speak. So we manage the expectations accordingly, but it's a pretty slim number of polymers that we would engage with for that type of application, knowing that it may need to be white or a vibrant color, which is pretty difficult to stabilize. And then choosing from a select group that's able to be colored those colors. And I think that bears, digging into as well. There's certain polymers on the market that are very UV stable that just won't be able to consistently be colored bright colors and stay bright colors. It tends to be very bright or fluorescent materials that tend to have the most noticeable color shift, even independent of how their delta E may read on a colorimeter or a spectrophotometer. So we take that in stride, but typically we're looking at minimum of a year or two performance for a cooler type of application. Next question, Andrea. Will the physical properties of ABS or PC-ABS be seriously affected by UV light or just the color?
They both would be, yeah. So PEC, ABS discolors quickly. It would also embrittle and be impacted quite a bit. It has both of the materials tend to have good impact to begin with, but because of the embrittlement nature of when it starts to degrade, it'll start to lose some of that performance. And so both color and properties will shift greatly when they're attacked by UV.
In the case of ABS, it's typically the butadiene rubber component, the B in the acronym, that is breaking down under UV exposure. And as that butadiene starts to oxidize, you lose the ductility, which ultimately results in a loss of mechanical properties as well as the color. So that's kind of the rationale behind the scenes as to why ABS isn't commonly chosen outside for outdoor use. There is a similar variant in ASA that uses, it's kind of a cousin to ABS, uses a different rubber package, which is why you're able to get enhanced UV stability. But the difference from butadiene to ASA's rubber is it's not quite as robust to begin with, so there is a give and take when we're trying to select some materials that may have enhanced UV stability. At times we're giving up a little bit on ductility or thermal performance or what have you, depending on what other polymers we're trying to shift to. The example here of a customer that's blow molding H2P birdhouse gourds for home martins. What would be the best UV stabilizer for an HDPE birdhouse, and at what letdown?
I think that comes back to getting one that would be compounded in. Your howls are going to be the best for it. You could, depending, because if it's a birdhouse, depending on the expectation, you could potentially get away with adding in carbon black to the 2% loading or maybe a little past that and be okay. Or if the expectation is that we need it to last 5, 10 plus years, then maybe we get a compounded option that has UV stabilizer already in it, which would be more in a HAL format.
Yeah, just for sake of reference on that topic specifically, I've got a data sheet up for one of the additives we distribute for UV stabilization, specifically for polyolefins. It's made with a polyethylene carrier, and its letdown ratio recommendations are 1 to 3%. And we can get your recommendation offline as well. If you don't mind shooting Andrea or I an email coming out here, we'll shoot over a recommendation and get you, tagged up with our sales team in terms of what cost and availability and things like that would look like, Greg. Next question, Andrea. Do HALs have downsides such as corrosion to the screw or barrel of the molding machine?
That's a great question. I would imagine there's some downside to it. I don't, off the top of my head, I don't know. I'm sure there's some, you're putting additional chemistry into it. Maybe you're aware of if it's more abrasive to that type of stuff or corrosive. I'm not aware of it, but I'm sure you're giving up something.
In my experience, we haven't had any processing related issues or machinery issue with some of the HALs that we've used in the past. Typically, the biggest barrier to entry at the beginning is the cost compared to either other stabilizers or certainly the cost compared to something as simple as carbon black. It tends to be, considerable increase in cost to consider a house package over others. Oh, sorry, Andrea, for the birdhouse score question, they were light gray in color for their customer requirements. So it sounds like carbon black would be out. So we'd be looking to a more traditional additive that would allow for other colors to be used.
Got it.
Next question, what particle size of carbon black is deemed appropriate for absorbers, realizing that higher loadings would allow for a larger particle potentially?
It's a good question. I don't know if we go through and distinguish the particle size of carbon black that's in ours. You can use standard master batch color that contain carbon black to do it. I don't know the particle size of that. But for the 2% recommendation, I mean, that's as simple as using a universal color that has, 50% carrier and 50% carbon black, and that can achieve a couple year type performance for the material itself. I'm not aware of the particle size.
I'll see if I can find anything. This question came up a long time ago in my tenure with Chase, at least, probably 10 years ago or so. Um, and it wasn't something that our suppliers had put out per se. Andrea's right. Typically, the particle size used in a lot of our UV stabilized resins or additives is not disclosed to even us as a distributor, nor is it listed necessarily on data sheets or SDSs or anything like that. That being said, there was a study that one of my colleagues had seen some time ago talking about the different types of particle size of carbon black and the advantages of each pending their intended use. Overall, the trend was that smaller size carbon blacks would have greater UV stabilization, but I can't recall specifically what particle sizes were all compared and where it fell within the spectrum. So if we can find something similar, we could send it along. Carl, if you wouldn't mind sending us a note at Andrea's email there, we can dig into it a little further for you. Next question, Andrea. Do we offer accelerated weather testing of parts as a service?
We do not, as Chase. We do have partnerships with third-party labs, though, that can complete those types of testing, depending on what you need and what their capabilities are. We work with companies like Intertech and the like to have testing done. And so depending on what you need to have done, as long as we can get a good idea of that, we've worked with labs like that in the past, or had our customers work with them directly. Whatever ends up working out best for whatever program, whatever is being worked on, it could be done. We at Chase, though, do not do it.
Do additional UV absorbers or housed ever need to be added to the black colorant, or is the carbon the sole UV absorber needed, mostly regarding polyolefins?
That comes down to the expectations. The carbon black will be helpful for a decent performance, but they do get used up. And so hows are outperform them, they outlast them. And so if we need extended performance, we're talking we want it to last 5, 10, 15 type years-ish. Again, we don't love putting timelines on performance for additives per se because of all the factors that go into it. But if you need something that's robust, that's going to last quite a few years, a combination of the additives could be necessary to achieve that.
Next question is increasing the percentage quantity of the stabilizer also increase the time it will keep the polymer stabilized, i.e. doubling the stabilizer doubles the protection time, for example.
It would not work like that. There would be where you get to the point where there's a trade-off. So if you start adding too much of it in, you're going to start to have issues potentially with the performance. You might start to affect its overall performance by adding too much of the additive in. You might make it difficult to process. You're going to start to give up certain things. You're going to hit a certain point where it doesn't make any sense to go any further. And typically at the percentages that are recommended and or already compounded in, those are going to be about your optimal letdowns based on historical studies and understanding of the materials and how they interact with those additives. And so if they tell you to put in 2% and you jump it to 4 or 8, it doesn't magically linearly, wow, barely we're not pronouncing that word. It doesn't give you proportionally 2 or 4 times better performance. It doesn't end up working that way.
I think as long as we're within the recommended range for utilization, though, say from the 1 to 4% recommendation range, if we were to add 1% compared to 3%, theoretically the 3% should be more stable. Would you agree, Andrea?
Yes. It would also, I'm assuming it also helps a little bit, especially if it's an additive after the fact. It would also help with your mixing of it and making sure it's more uniform across the part. I'm sure that that helps with it as well. Make sure you get a really good mix, because if you're the one, you're buying the additive, you're buying the carbon black, whatever, and you have to have it mixed at your machine, there's a chance it's not going to be the most uniform of mixing, and so it would help in that regard. And then those areas that may or may not have had a little bit less of it in that area that wouldn't have been as protected, it would result in better protection.
And then Mike, I see we got some back and forth here on the carbon black. Let's take your question offline to see if we can better describe what we're seeing in terms of carbon black and its UV absorbing tendencies. Thanks as well for the rest of the team, though. Got some input here from one of the attendees, Mike, that's chimed in on the size of the particle for carbon black. That the rationale for the smaller particle sizes being chosen is that you end up getting more surface area of the carbon black to convert UV to heat, and that 19 nanometers is typically regarded as a good compromise to avoid agglomeration, as smaller particles are prone to. So thanks, Mike, for the additional input for the rest of the group as well.
Thank you.
All right, that looks like all of our written questions. Our hands up question has left the chat, has left the webinar. So maybe we'll get that in an email. But we do want to thank you all for taking time out of your busy schedules to attend this Chase the Knowledge webinar. We hope it was informative. Looks like it was, and that it was a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. You had her information posted on the previous screen. Thank you all for attending. We hope to see you at our next Chase the Knowledge webinar in December. Thank you. Thanks, Andrea. Thanks, Jason.
Thanks, Sherry. Thanks, Jason.